Welcome back. So we were talking about stochastic gradient descent and gradient descent algorithm, and we talked about how they perform when our loss functions are convex. But that's not typically the case when we are optimizing parameters of a deep learning model. So we want to go beyond the convexity assumption, okay? And we're going to talk about a property which is called the smoothness that sort of facilitates answering these kind of questions. Okay, so we talked about, as I mentioned, gradient descent and SGD and how they perform if the function is convex. In a nutshell, our result says that if the function is Lipschitz, again, that means that it has bounded sensitivity. Both of these methods satisfy the same rate. But note that the notion of convergence is slightly different. For gradient descent, we said that the average suboptimality gap was bounded by let's say 1 over the square root of t if I ignore the other constant parameters. But for SGD, the expected average suboptimality gap was bounded by this rate. Okay. All right. But deep learning problems are typically non-convex optimization problems. So our goal is to relax the convexity assumption. Okay. Unfortunately, this is a very difficult goal and very ambitious goal to achieve. So our approach will be the following. First of all, we're going to start with simpler notions of convergence, meaning instead of focusing on the suboptimality of a specific solution, we're just going to assess whether that's a stationary solution or not. Basically, a solution at which the gradient is 0 or near 0. Then, when we gain some insight on the performance of gradient descent, SGD, and more advanced training algorithms, we're going to start, as we progress in the course, we're going to start identifying certain structures that exist in deep learning optimization problems, and we're going to leverage those structures to strengthen the convergence notions and therefore provide stronger guarantees for our training algorithms. All right, but first thing first, we're going to start, as I mentioned, with basic assumptions, and that requires basic notions of convergence. So what is our goal? Our goal is to, again, focus on approximate first-order stationarity, meaning instead of focusing on suboptimality of a solution or expected suboptimality of the solution, we're just going to assess whether that solution has a small gradient or not. Okay. So, and again, this is a picture you should have in mind. So all of these points are points at which the gradient is 0. Okay. Ideally, we want to ensure that we find solutions like this, but this condition could mean that the solution is also a local maximizer. But intuitively, gradient descent and other methods that follow a direction of descent are not going to converge to solutions like this, which are highly unstable. Okay, because if I just perturb the solution slightly, I can reduce the function value. This is something we're going to get back when we talk about stronger notions of convergence later on in the course. All right. So this is our notion of convergence, and this notion, when you look at it, requires that the gradient to be well defined. Okay, it requires the existence of the gradient. Now, this is something that will require us, in turn, to resort to a different notion to characterize the sensitivity of the function. Previously, we were talking about Lipschitzness, right? Which basically meant that if I change the parameter value slightly, the function value doesn't change much. Here, we need a different notion, okay? And that's called smoothness. All right, so formally, we call a function L smooth if its gradient is L Lipschitz. Okay? So basically, again, if I change the parameters slightly, now the gradient value doesn't change much, as opposed to function value. Okay? And then there is a constant L that determines the degree of sensitivity. Okay? So if L is large, that means that the gradient is more sensitive with respect to changes in the input. So therefore, the function is also in some sense more sensitive. On the other hand, if L is very small, or in the extreme case is equal to 0, then if I change the input, the gradient doesn't change much. Therefore, my function has lower sensitivity as well. Okay. Now, you should also think about this condition as some form of a slope, like we talked about when we introduced the concept of Lipschitzness. Okay, Lipschitzness implied that the slope of the function or the tangent line at the function is bounded. Smoothness, on the other hand, means that the slope of a tangent line at the gradient, in particular, the second order derivative, or the Hessian, is bounded by L. More formally, because Hessian is like a matrix, this means that if our function is twice differentiable, all eigenvalues of the Hessians are bounded. Okay, so if a function is smooth, is L smooth, all eigenvalues of the Hessians are bounded by L. So that means that they are nicely located between minus L and L. Okay. Note that this doesn't require the function to be convex, because the eigenvalues can indeed be negative. All that says is that the curvature of the bounded function is bounded. Okay. Let's go over some examples first, and then we'll talk about the smoothness a little bit more. Okay. So imagine that my function is something like this. This is basically a quadratic function. Now I want to find the smoothness constant, or basically determine whether the function is smooth or not. Okay. So what we need using the last discussion is to show that the eigenvalues of the Hessian are bounded by L. Okay. So this basically requires us to find the Hessian. So let's find the Hessian. Okay. Now it turns out that the gradient of this function with respect to x is ax. Here am I assuming that a is symmetric. So a symmetric. And it turns out that again, if I take the gradient one more time to find the Hessian, so this is basically the Hessian, this becomes A. Okay. So as long as this matrix A has eigenvalues that are bounded, the function will be smooth. For instance, let's imagine that the A is some diagonal matrix. So I have 2, -1, 0, 0. So for diagonal matrices, you may know from linear algebra that the eigenvalues are basically the entries that are located on the diagonal. So one eigenvalue is equal to 2, another eigenvalue is equal to -1. Okay. Again, this function is a function that's non-convex, but the eigenvalues are basically the absolute value of the eigenvalues are less than or equal to 2. This means that the Lipschitz constant is equal to 2. Okay, so therefore the function is Lipschitz. The function is smooth, and the smooth constant is equal to 2. All right. Now let's go over the second example, and that's a scalar function, which is just the exponential function. Okay, and this is something we saw before when we talked about the Lipschitzness, and there we saw that if we don't restrict the domain, the function is not globally Lipschitz. And this is also the case here, because to find the smooth constant, I have to find the Hessian basically. So the first order derivative is again ex, the second order is also e to the power of x. And this is not bounded, because as x goes to infinity, the second order derivative also goes to infinity. Okay, so therefore the function is not smooth, and this does make sense, right? It is a highly sensitive function to the changes in its input. On the other hand, let's say I restrict the domain such that, let's say, x belongs to some interval ab. Then I can bound the smoothness, right? So in that case, because I'm restricting the domain, the largest the smoothness parameter can be is just e to b. So therefore, any function with a restricted domain, as long as it's nice and differentiable, you can assume that it's also smooth, but the smooth constant could be very, very large. And one implication of that, as we'll see, is that the guarantees that we establish are going to be sometimes very, very loose and conservative. All right. So hopefully these two examples help you to gain more insight about smooth functions. But let's also discuss them a little bit more, because this discussion is going to provide some tools that are very frequently used when analyzing optimization algorithms, especially those used in the optimization of deep learning models. Okay, so we said that one way to think about smoothness is that all the eigenvalues are bounded. Okay, so it doesn't say that they are negative or positive. It just says that the absolute value is bounded by some constant, and that constant is nothing but the smoothness constant. Okay, so this basically means that the function has bounded curvatures, both from above and from below. So this basically means that when a function has a bounded curvature, by that we mean that we can upper bound the function at any point by a convex quadratic function, and also we can lower bound the function at any point by a concave quadratic function. So let me try to demonstrate this here. Let's say this is the x-axis, okay, and then I have some function like this. Okay. Now imagine that this is point x. Okay. Now I consider a quadratic function. As you can see here, I can find an upper bound, a global upper bound on the function at this point x. Okay, and this is my function. Let's call this function f of y. Okay, so this is the y-axis. So this is a convex quadratic function because the function is curving upwards. Okay, the curvature is essentially positive. Similarly, if you give me any other point x here, I can find a concave quadratic function that lower bounds the function globally. Okay. Therefore, this is an example of a function which is a smooth. Okay. All right. So more mathematically, these two conditions, meaning that I can upper bound the function globally by a convex quadratic, and I can lower bound the function globally by a concave quadratic, can be written using these two inequalities. Okay, so this basically, the first one, it says that as a function of y, again, I can find a quadratic function. So this is basically a quadratic function of y. So I have my global upper bound. And this one says that as a function of y, I can find a global lower bound on the function, which is a concave quadratic function. Okay, so this is basically a quadratic function of y. Right. So these two conditions are very. You can actually take them as equivalent definition of a smooth function. Okay, so you can say that a smooth function is a function is smooth if you can find such global upper bound and lower bounds on the function. So these two inequalities are very, very useful, as I mentioned before, in analyzing optimization algorithms used to optimize parameters of a deep learning model. All right. So this is something we're going to use in this lecture to analyze the performance of the two algorithms we have seen in this course. The first one is gradient descent. The second one is basically the stochastic version of gradient descent, or SGD. Okay. So let's see what our theorem says. Before diving into the proof, we're going to provide some insights, and then we'll see how we can approach proving these theorems while leveraging the smoothness property of the function. So let's define this notation first. Let this delta to be the initial suboptimality. Okay. Now for gradient descent, we have the following theorem. If our function is L smooth, then if I run gradient descent with this specific step size, which is inversely proportional to the smoothness constant, it's going to satisfy this bound. So what does the bound say? It says that the accumulated norm of gradients is bounded by this ratio. It is proportional with L, meaning that the more sensitive the function, the larger the bound. It is proportional to the initial suboptimal gap. The further away you are from an optimal solution at initialization, the larger the bound. So these are both intuitive. And finally, it is inversely proportional to the number of iterations. The more you run your algorithms, the closer you get to a stationary point, basically. And what I have here on this side, you should think of it as, again, a notion of stationarity, okay? And we'll talk about this a little bit more in the next slide. All right. Now, in terms of the O notation, meaning that if I only care about the dependence on the number of iterations, the dependence is basically 1 over t. So this is an instance of a sublinear rate. Okay. All right. So we also have a similar theorem for stochastic gradient descent. Okay. So we again assume that our function is L smooth, but we also now have assumptions, and these are assumptions we saw before as well when we analyze SGD for convex function. We're going to assume that we have access to an stochastic first order oracle, meaning an oracle that returns to us unbiased estimators of the gradient in each iteration with bounded variance. And in addition to that, we assume that the samples we use in each iterations are statistically independent, meaning that, again, the mini batches we use in each iteration of SGD are independent. If we run SGD with this step size, which is a little bit more complicated than what we had before, we're going to satisfy the following bound. The expected average norm of gradients is bounded by 2 terms. Again, like before, we have one term which is identical to the performance of gradient descent, but we have another term which depends on the variance of our oracle. If our oracle is perfect, meaning that the variance is 0, this term will vanish. Otherwise, the higher the variance, the larger the second term in the performance of SGD. Now, in terms of the O notation, this is 1 over the square root of t, okay? And this is something new that we didn't see when we were comparing GD and SGD for convex functions, okay? So previously, when our function was convex and Lipschitz, both essentially achieved the same rate as a function of t. In this case, however, that's not the case. We can see that gradient descent error goes to zero faster than SGD in the worst case, okay? Because 1 over t, when t is large, is significantly smaller than 1 over square root of t. All right, so let's have a short discussion about these theorems and their statements. So first of all, the results are again dimension-free, meaning that the size of our parameters, which we use d to denote it, doesn't appear in the bound at all, okay? But again, we should expect that d appears implicitly through parameters of relevance, such as the variance of the oracle or the smoothness constant, etc. The step size or the learning rate again plays a regulating role. So the sharper the function, the more sensitive the function, the smaller step size we have to use to ensure that we are still able to approach a stationary point. And we also see it here. But for SGD, there is also like a nice dependence on the variance. So this basically means that if the variance of the oracle is large, eta is chosen to account for that. So essentially, we're going to be more careful with the steps that we are taking, because each step is now a little bit more noisy than before, okay? So, and that means that we're going to adopt a smaller learning rate. Now, the statements were about accumulated norm of the, or average norm of the gradients that we encounter while we run SGD and gradient descent. Like before, there are certain procedures that we can use to output a solution, okay? The first procedure is to output the last solution, or essentially the best solution, okay? And this is what we do in practice. And the theorem doesn't establish anything about the performance of this approach when generating a solution. And this is sort of consistent with our previous discussion on the performance of gradient descent and SGD on Lipschitz and convex functions. The second approach is to sample one iteration at random, okay? So in particular, for this, the average norm of the gradient that we saw, so something like this, this could be thought as an expectation when you sample a solution uniformly at random. And this is identical to what we saw before when we talked about convex functions. Okay, so using this approach, when you sample one iterate uniformly at random, you can basically show that the expected norm of the gradient is bounded by this for gradient descent, and the expected norm of the gradient is bounded by this other term for a stochastic gradient descent algorithm. Now, another way to interpret the result is to talk about iteration complexity. Essentially, if I want the error to be less than epsilon, how many iterations do I need to run my algorithm? And it's not hard to see that for gradient descent, the iteration complexity is given by this, so it's 1 over epsilon, whereas for SGD, it's basically 1 over epsilon squared. Again, this means that for the same performance, if you are shooting for epsilon, you may have to run SGD for more iterations than gradient descent. All right, now let's look at this one again. For stochastic gradient descent, we have two terms here. We have one term which is referred to as a higher order term. So this is the first term that matches the performance of SGD. And we have a dominant term, which is the second term, which is due to stochasticity. And these are defined, again, based on the dependence on t. The first term is much smaller than the second term in terms of t. Therefore, we refer to it as the higher order term, and we refer to the second term as the dominant term. Okay, and this is why the iteration complexity of SGD is actually worse than the gradient descent, because despite the higher order term matching gradient descent, the dominant term is actually much larger, meaning that the algorithm is going to suffer from a worse iteration complexity. And finally, a natural question to ask is whether these bonds are tight or not, because at the end of the day, what we are saying is that the worst case performance is bounded by a certain quantity, certain bond, okay? But this is the worst case performance. In practice, many times, we are very far from a worst case scenario. And that means that these algorithms could indeed converge faster than the rates that we are stating here. Okay? But in the worst case, you can do better than this, unfortunately. However, as we're going to talk about later in the course, when we talk about more advanced training algorithms, we can leverage structures that exist in our optimization algorithms when we are optimizing deep learning models to show that certain training algorithms are actually provably better than SGD. So we'll be able to improve upon this bound when we leverage more structures. So in the next video, I'm going to talk about another benefit of smoothness, which essentially provides us a way to look into gradient descent and potentially design more general and even better algorithms. I'll see you next time.